Okay, so 11.4 is on the comparison tests. Right? The comparison test. Well, sometimes they call it the basic comparison test. It depends on what book you're taking Calc 2 out of. The basic comparison test or just the comparison test. Okay, there are two comparison tests, so sometimes they call this one the basic one. Okay, suppose the summation of a sub n, the series a sub n and the series b sub n are series with positive terms. Okay, so they got to be positive terms here. Okay, one, if b sub n, the series b sub n, is convergent, and b sub n is greater than or equal to a sub n for all n. Okay, so the terms of b sub n are bigger than the terms of a sub n. Then a sub n is also convergent. Okay, so let's draw a little diagram. That's black, I believe. Let's do black. Okay, so say that the terms of b sub n, so we'll let green be b sub n. Okay, the terms of b sub n are always bigger than the terms of a sub n. We'll let a sub n be red. Okay, and if, oops, let's do this the other way. Sorry. If b sub n is bigger than a sub n, so b sub n is bigger than a sub n for all the terms, and if b sub n converges, okay, then that's going to force a sub n to also converge. Okay, it's kind of getting squeezed between there. So we're saying, look, if the terms for b sub n, okay, are getting smaller and smaller and smaller, and it does have a limit, okay, then a sub n also converges. Okay, so number 2. I don't know if I like that picture or not. Whatever. Okay, number 2 here. Okay, if a sub n is divergent, okay, this time. So if b sub n converges, and b sub n is the one on top, then it's going to force a sub n to converge. But if a sub n, the smaller one, is divergent, and b sub n is greater than or equal to a sub n, for all n, then the summation of b sub n is also convergent. I'm sorry, divergent, is also divergent. Okay, so picture on this one would look like this. Okay, again, a sub n is on the bottom. Okay, but it's diverging. Okay, the sum is diverging. Okay. And then yeah, that's the sum. The sum is going up. Okay, and it's diverging, and that's a sub n. Then anything that's bigger than that will also diverge. You know, if we keep adding terms together, it's also going to diverge. A b sub n. Again, I don't like this. I am going to get rid of this one. I don't like the picture on that one. Okay, because if it converges, it's going to converge to a limit, and it said that these terms were positive. So what I'm going to have it do is I'm going to have it say, look, if b sub n converges, then a sub n, which is always less than b sub n, also converge. Okay, that makes me more happy. So we get this sum, right? This partial sums. Okay. The summation of b sub n is going to converge. Okay, number one. Determine whether the series summation n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 converges or diverges. Okay. So we want to compare this with something that either we know converges or we know diverges. We want to make sure that, you know, it's set up correctly. So I know that, you know, let's let this be, you know, the first series. And I want to compare that to this series here, which is 5 over 2n squared. Okay. Now I know that this series converges because this series is a p series with okay, p equaling 2. Okay, just happens to have a coefficient in front of it of 5/2, but it's still a p series. So convergent. Okay. I want to compare these terms, 5 over 2n squared to 5 over 2n squared plus 4n plus 3. Now, if I take a number and I divide by a bigger number, then don't I get a smaller value? Right? If I'm dividing more values to that number, then I would get a smaller value. Okay, because and we don't have to worry about fractions here because n is greater than or equal to 1. Okay, n is actually, I just write it as the n is an element of the natural numbers. Okay, so we know that that holds. So if this series 2n 5 over 2n squared converges, then because that's the bigger one, of the two, remember, go back to the picture. Okay, if that series converges with my partial sums, okay, 5 over 2n squared will converge, then something that's always smaller will also converge. Okay, 5 over 2n squared plus 4n plus 3. Okay, that's also going to converge. Okay, if this converges, then this guy will converge. I'll write on the same line. 5 over 2n squared plus 4n plus 3 also converges. Okay, by the comparison test. Okay, by the comparison test. Okay. I'll just put a since there. That's my answer. Okay, since that thing converges, then that thing also converges by the comparison test. Okay. Sometimes the comparison test kind of goes the wrong direction. Okay. For example, if I tried the previous problem and it was 5 over 2n squared compared with summation 5 over 2n squared minus 4n plus, or minus 4n minus 3, then we couldn't use the comparison test. The comparison test would fail us because, you know, this thing is slightly bigger, slightly larger, okay? And so we couldn't use the comparison test. But we do have another test that we can use in case we come up with this type of scenario or other scenarios where we're like, hey, can we really use a comparison here? And the comparison kind of goes the wrong way. So yeah, and that's called the limit comparison test. We cannot use the comparison test, but can use the limit comparison test. So let's define the limit comparison test. The limit comparison test says, suppose that the summation of a sub n and the summation of b sub n are series with positive terms. If the limit as n goes to infinity of a sub n over b sub n equals a constant, then both, constant greater than 0, it's got to be a positive constant, equals a positive constant, then both series converge or both diverge. Okay, so they either both converge or they both diverge. So let's use the limit comparison test with this one that we couldn't use the basic comparison test on. So I'll let a sub n be equal to, what do I want? I want, really doesn't matter, but I'll put the simpler one on top. Summation of 5 over 2n squared. Okay, and I'll let b sub n be equal to 5 over 2n squared minus 4n minus 3. Okay, and so we want the limit as n goes to infinity of 5 over 2n squared all over 5 over 2n squared minus 4n minus 3. Okay. So now I'm just going to flip. This is going to be equal to the limit as n goes to infinity of 5 over 2n squared times 2n squared minus 4n minus 3 all over 5. Okay, so this is equal to the limit as n goes to infinity of 2n squared minus 4n minus 3 all over 2n squared. And I can break this up over a common denominator. Limit as n goes to infinity of 2n squared over 2n squared minus 4n over 2n squared minus 3 over 2n squared. The n squareds cancel here, leaving me with just 1 minus one of the n's cancels there, leaving me with 2 over n minus 3 over 2n squared. Limit as n goes to infinity. That goes to 0. That goes to 0. Oops. Okay, that goes to 0. Okay, and so I'm just left with 1, which is a constant greater than 0. Check. And so they both converge. Since a sub n equaling 5 over 2n squared converges because it's a p series, p equal to 2, then b sub n equaling 5 over 2n squared minus 4n minus 3 also converges by the limit comparison test. Okay, and then what's my answer? The whole thing, the whole sentence. Okay, for these tests, you need to have an answer that is a sentence. Okay, a complete sentence. Okay.
Professor, this is Sekla. I came in.
Yeah. Question?
No, I just came in a little late.
Oh, okay. Okay. So that was number 1, right? Number 2? That was number 2. Okay. That was actually just an example. Okay, so let's go to number 2 here. Okay, test the series summation n equals 1 to infinity of the natural log of n over n for convergence. Okay, so what are we going to do? Well, we're going to compare with the summation n equals 1 to infinity of just 1 over n. Okay, we're going to compare with that. Okay, because what do we know about 1 over n? 1 over n is the harmonic series, and it diverges. It diverges. And so I want to compare these values, okay, with some of with the values that I'm getting for natural log of n over n. Well, if I look at the summation of natural log of n over n, okay, as n equals 1 to infinity, and I compare that with 1 over n equals 1 to infinity, okay, this is going to be the natural log of 1 over 1 plus natural log of 2 over 2 plus natural log of 3 over 3 plus natural log of 4 over 4 plus natural log of 5 over 5 plus forever. This is going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, okay, plus 1 over 5 plus 1 over 6 plus dot dot dot. Okay, just we'll stop at 5. Okay, plus 1 over 5 dot dot dot. Now, if I look at this initially, this doesn't go the right direction. Okay. Initially, natural log of 1 over 1, that's 0. So this thing becomes 0 plus, and then natural log of 2 is 0.693 over 2. And then natural log of 3 is 1.099 over 3, plus natural log of 4 is 1.386 over 4, and then plus 1.609 over 5. Okay, so initially, things don't look very promising until we go past the first two terms. These first two terms are smaller, but every other term in natural log n over n is bigger. Okay, so compared to, so it's just the first two terms that don't work. But now these terms are always bigger. The top terms are always bigger than the bottom ones. So how do we reconcile that? Well, instead of starting with 1, I'm going to start with 3. And I'm going to say, well, from n equals 3 to infinity, okay, because eventually, okay, this thing is going to, it's okay because this thing's going to diverge anyway, the harmonic series, but from n equals 3 on, the natural log of n over n is greater than, okay, for every term, maybe I'll just say this. Natural log of n over n is greater than 1 over n for all n greater than or equal to 3. Okay, so if we start at 3, then we can compare, the summation n equals 3 to infinity of natural log of n over n to the summation n equals 3 to infinity of 1 over n. And since the natural log of n terms are always bigger than what we know to be a convergent sequence, okay, so 1 over n is small, but it converges, or diverges, sorry, and natural log of n is, it goes like this, actually, it goes like that, okay, and then this becomes natural log of n over n, and so what we're just saying is we're saying, just start at 3, okay, so we compare that to that, and since the summation n equals 3 to infinity of 1 over n diverges, since this diverges, which means it's just going to get bigger and bigger and bigger, okay, forever, then the series n equals 3 to infinity of natural log of n over n also diverges. Okay, and if something diverges, does it really matter if I add this back onto it? You know, if I add 0.693 over 2, or, you know, if I say, oh, well, 0 plus natural log 2 over 2, okay, plus a divergent series. Okay, if I take a divergent series, the sum of a divergent series, and then I add more to it, is that going to make it any less divergent? No, this still diverges. Then the summation n equals 1 to infinity of natural log of n over n, we back it out to the first term now, diverges. Okay, so that one's divergent. Okay, number 3. Test the series summation n equals 1 to infinity of 1 over 2 to the n minus 1 for convergence. Okay. Okay, so what do I want to compare this with? Okay.
Just a P series, 2 to the n.
Yeah, but P series is not 2 to the n. A P series would be n squared, right? But you're on the right track. I would want to compare it.
Professor,
Yeah,
could we compare it to 1/2 to the power of n?
yes, yes. So we could compare it to 1/2 to the power of n, which we have seen does what? Does anyone remember what this does?
Converge.
Yeah, it converges. Why? I actually know what it converges to. This converges to 1. Why is it converge to 1? It is a what type of series?
Geometric series?
That's a geometric series. Okay. Geometric series. It's a geometric series with R equaling 1/2, which is less than 1. So I don't really need to calculate what it converges to. I just remember that it does converge to 1 because we keep adding, 1/2 plus 1/4 plus 1/8 converges to 1. Okay, but the geometric series with R equals 1/2 is less than 1, so it converges. Okay, so this is convergent, and then okay, and so how are we going to prove that the other one also converges? We have 2 tools in our toolbox, right? We have the basic comparison test or the limit comparison test. Which one are we going to use here in this case? Basic comparison test or limit comparison test? If we look at the terms here, 1 over 2n compared with 1 over 2n minus 1, which one's bigger and which one's smaller? Inequality should go like that, right? Because if you divide by a bigger number, or sorry, if you divide by a smaller number, sorry, the inequality should be reversed. My bad. Okay, because if you divide by a smaller number, you get a bigger number. No, that's right. Yeah, if you divide, I had it right. Okay. What I get for second guessing myself. Okay, so if you divide by a smaller number, you get a bigger number, right? So we know that this thing is convergent. However, all of the terms in this one is bigger than something's convergent. So can I use the basic comparison test? Can I use the comparison test?
Use the limit comparison test.
Yeah, I can't. Yeah, exactly. Thank you, Con. I cannot use the basic comparison test because it doesn't go the right way. Okay, if I have something that's convergent, but then I have something that's bigger than that, well, that doesn't prove that that thing is convergent. Okay, it would have to be smaller. The inequality goes the wrong way. But I can use the limit comparison test. Okay. I can say that the limit as n goes to infinity of 1 over 2 to the nth over 1 over 2 to the n minus 1, okay, the limit of that, is equal to the limit as n goes to infinity of 2 to the n minus 1 all over 2 to the n, which is equal to 1 to the limit equals to the limit as 1 minus 1 over 2 to the n. Okay, as n goes to infinity. Okay, and so that goes to 0, and so I'm left with 1, which is greater than 0. It's a constant greater than 0. And so therefore, okay, just greater than 0. Gosh, I can't write. Okay, so therefore, okay, so this is my sentence. I always have to have a final sentence on any of these tests. Therefore, by the limit comparison test, since the summation of 1 over 2 to the n power n equals 1 to infinity converges, then the summation n equals 1 to infinity of 1 over 2 to the n minus 1 also converges. Oh, there's my answer. That sentence. Okay. Okay, that's 11.4. Let's jump into 11.5, which is alternating series. Okay, alternating series. Okay, before we do that, I want to just kind of recap, okay, on what have we learned so far, okay? What are my tests that I've learned so far? How can I test if something is convergent or divergent? Okay, so my first test that we talked about was if it's geometric with r, with the absolute value of r less than 1. Okay, if r is a fraction, then it converges. Converges, otherwise diverges. Okay, number 2. Okay, what was the second one that we learned about? Did geometric. Okay, second one, I want to say that it was the divergence test, but there might have been another one before that. Let me think. Geometric series test. Yes, I like that. Okay. Yes, there was one before that. There was one before that. Okay, harmonic series. Okay, and we know the harmonic series diverges. It's kind of its own test. Okay, it's just for one series. Number 3 is the divergence test, or what we call the nth term test. And the divergence test said that if the limit as n goes to infinity of a sub n does not equal 0, then the series diverges. Basically, if the terms don't get smaller, the series diverges. Okay. Okay, number 4. Number 4 test was the integral test. Integral test. Okay, we talked about the integral test last time. Okay, and then number 5, we have the comparison test. We'll call this basic comparison test. Oh, by the way, what did the integral test say? That if the integral of f of n, okay, or f of x dx, okay, from 1 to infinity, if that converges, then a sub n converged, then a sub n summation converges. And then if this thing diverges, then a sub n diverges. Okay, so if the integral converges, then the series converged. If the integral diverges, then the series diverges. Basic comparison test, okay, we just went over, says that if I have a sub n and b sub n, okay, and if b sub n converges and is bigger than a sub n, then a sub n also converges. Okay, b sub n greater than or equal to a sub n, and b sub n converges. Oops, my writing's getting a little small. Okay, and b sub n converges, then a sub n converges. Okay, but if a sub n is the smaller one, okay, and it diverges, then b sub n also diverges. Okay, if a sub n diverges, then b sub n diverges. Okay, and then test number 6, okay, was the limit comparison test. Okay, and the limit comparison test that if I have a sub n and b sub n, and the limit as n goes to infinity of a sub n over b sub n is equal to, not 1, is equal to a positive constant, then they both converge or both diverge. Okay, and then we're going to add a 7th one. We're going to have 9 in total. We're going to add a 7th one in 11.5. Okay, and then 11.6, we're going to add 2 more, and that'll be it. That'll be all 9. You'll have all 9 tests, okay, available for your exam. Okay, so we're gonna have 9 of these tests. Okay, and we're gonna add number 7 right now. Okay, so the alternating series test, maybe I'll put it right here in our list. Alternating series test. Okay, the alternating series test says that if you have a series n equals 1 to infinity, and it alternates like -1 to the n minus 1 of b sub n, okay, some sort of alternating series. Okay. Okay, so then if my terms are always decreasing, if my terms always get smaller, okay, the absolute value of my terms basically is what I'm saying. If the terms, if every single term is smaller, okay, then the one that came before it, if b sub n plus 1 is less than or equal to b sub n, okay, let's say for all n, and if the limit as n goes to infinity of b sub n equals 0, meaning that these eventually get so small, they're always going down, and they get so small eventually that they go to 0. If those two are correct, then the series converges. So it's kind of like the anti. Remember, we couldn't say that this is a test for convergence. This by itself is not a test for convergence. If it doesn't equal 0, then it diverges. That's the divergence test, okay? So that by itself doesn't test convergence. And we said that our counter example to that was the harmonic series. But here's the big but. But if the harmonic series alternates, then it converges. Okay. So let's write that over here. Okay. Okay. So the alternating, oops, a little bit too small. Okay, the alternating harmonic series, which is -1 to the n minus 1, okay, of n equals 1 to infinity. I do n minus 1 because I just want the first term to be positive. Okay. If I did n, then the first term would be negative. So I just do n minus 1, then the first term is positive. 1 over n, the alternating harmonic series is convergent since, okay, every term, every term b sub n, which equals 1 over n, okay, 1 over n plus 1 is less than or equal to 1 over n for all n. Okay, that's true. Okay, that checks. Okay, number 2, the limit as n goes to infinity of 1 over n equals 0. That checks. So by the alternating series test, the alternating harmonic, that is, i.e., 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus ... converges. Okay. Now why is it? Why did it make a difference between the original harmonic and the alternating harmonic? Why is that a thing? Why did one diverge and one converge? So we have the harmonic, which goes like this, right? This is just 1 over n, summation, right? We'll just do the 1 over n, and we'll just say we're going to add these terms, right? We're going to add that, add that, add that, add that, keep adding, and you know they get small, they go to 0. However, I keep adding, you know, more and more and more. So the picture of the partial sums, if I did the S sub n's, this is A sub n, the picture of the A sub n's. If I did S sub n, it would look like this. We would start off with 1, okay, and then we would keep climbing up. That would be the S sub n's. They keep going up. However, if I look at the A sub n's for the alternating harmonic, I'll call this B sub n, okay, where we have -1 to the n of times 1 over n, we still start at 1, okay, we'll make that 1, but then we go to -1/2, and then we go to 1/4, and or a 1/3, and then we go to -1/4. So every other one I'm subtracting off, okay, and that makes this thing converge. It goes to 0 much faster, because these are all negative values, so it kind of bounces up and down, up and down, up and down, and goes, okay? And so all the ones that are below the line, they're canceling values, okay? And so they're canceling a bunch of stuff. And so this thing goes to 0 much faster. Okay, and so what does S sub n look like? S sub n looks like this, starts at 1 again, but then it goes up, and then it comes down, and then it goes up, and then it comes down, and then it goes up, and then it comes down, and then it goes like that. Okay, and it converges. Okay, we add and then we subtract. We add and then we subtract. We add and then we subtract, and it goes like this. Okay, forever. Okay, but the thing does converge. It does hit a limit. Okay, because of all that adding and subtracting that we're doing. Okay, that was number 7. Okay, alternating series test. Okay, let's look at another one. Okay. This was example number 1, by the way. Alternating series test. Example number 2. Okay, let's just look at another alternating test. Okay, so is this guy, which is -1 to the n plus 1 over n squared over n cubed plus 1 convergent? Okay, does this thing converge by the alternating series test? Okay, well, let's see. We need to know, 1, if bn plus 1 is less than or equal to bn for all n. Okay, so, and what is bn? Bn is this thing here. This is b sub n. Okay, so let's do n plus 1 on this side. N plus 1 squared over n plus 1 cubed plus 1. Is that less than or equal to, okay, n squared over n cubed plus 1? Okay, b sub n is, and I'll put a little question mark here because I don't know yet. Okay, so let's multiply this out using, you know, this is a binomial, and we can use Pascal's triangle for this. Okay. Okay, so Pascal's triangle, this is n squared plus 2n plus 1 over n cubed plus 3n squared plus 3n plus 1. Okay, plus 1 is less than or equal to n squared over n cubed plus 1. Okay, again, is that true? Okay, so now I'm going to cross multiply. Okay, cross multiply. And I get n cubed plus 1 times n squared plus 2n plus 1. Is that less than or equal to n squared times n cubed plus 3n squared plus 3n plus 2? Okay. So multiplying all this out, I get n to the 5th plus 2n to the 4th plus n cubed plus n squared plus 2n plus 1. Is that less than or equal to n to the 5th plus 3n squared, n to the 4th, sorry. Come on, go, 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 go. N to the 4th plus 3n to the 3rd, okay, plus 2n squared. Okay. Okay, so okay. So I want to subtract the n to the 5th minus 2n to the 4th. I want to subtract everything from one side. Minus n cubed minus n squared minus 2n minus 1. Okay, and then minus n to the 5th minus 2n to the 4th minus n cubed minus n squared minus 2n minus 1. Okay. And again, I haven't proved this. I don't know if that's true or not, if this is true or not. Okay, so this side becomes 0. And I just want to know, is this side going to be 2n to the, or sorry, that's 1n to the 4th minus 2n to the 3rd, 1n to the 4th minus 2n to the 3rd minus n squared minus 2n minus, or plus n squared, sorry, plus n squared minus 2n. And I just want to know for all n that are part of the natural numbers, is this true for all n? Okay, this is plus, sorry, that's plus 2n cubed. N to the 4th, 2n cubed plus 2n, yeah, okay. So let's try 1. Let's let n equal 1. Okay, if n equals 1, I get 1 plus 2 plus 1 minus 2 minus 1, that's 1. 0 is greater than or equal to 1. That checks. Okay. Okay, if n is equal to 2, okay, then I get 16 plus 16, which is 32, plus 4, which is 36, minus 8, which is, go back to 24, minus 1, 23. And you could see very quickly that this thing is always going to be positive. Okay. You could do another one, but it's going to be even more positive because we have 3 terms that are positive. And so yes. Okay. This is true. So okay, so that was all to say that the first condition is met. Check. Okay, check, first condition. Now let's see if the second condition holds. What was the second condition? That the limit as n goes to infinity of a sub n is equal to 0. Does that work? Well, what's the limit as n goes to infinity of n squared over n cubed plus 1? Okay, let's use the L'Hopital's rule on this. Take the derivative of the top. I get 2n squared, just 2n. Okay, all over the derivative of the bottom, which is 3n squared. Okay, which is still infinity over infinity, but I could divide by an n if I wanted to. Okay, I could say that this is equal to 2 over 3n, which goes to 0. I'll put this below. I'm running out of room. Okay, limit of 2 over 3n as n goes to infinity, which does go to 0. That goes to 0, which checks. Okay, so therefore, the series n equals 1 to infinity of n squared over n cubed plus 1 is convergent. Oh, whoops, I forgot that it has to alternate. It would not be convergent if it didn't alternate. I'll tell you that right now. It would diverge. Okay, this converges -1 to the n minus 1 power, okay, of n squared over n cubed plus 1, okay, is convergent by the alternating series test. Okay. Okay, I'm gonna stop there for today. Okay.